it's paradise to me. Google it, YouTube it. All right, so chapter 9, infinite series. 9.1 is power series. Back in Algebra 2 is when it started, and then pre-calc, and then calc, we learned that if you have an exponential equation, we know that it's going to either decay or grow. And if it decays, the r has to be less than 1. So if that's the case, if r is between -1 and 1, or basically between 0 and 1, the sum of an infinite geometric series, so if there's an infinite amount of them, let's say we're going to go from 1 to infinity of 10 times 0.8 to the n. We can figure out what all of those add up to be by just finding the initial term and dividing it by 1 minus whatever your common ratio is, 1 minus r. So when it says a sub 1, it could be a sub 0, so it should be a sub initials. Think of that. Because sometimes we start at 1, sometimes we start at 0. So your first term over 1 minus r is the sum if it's an infinite series. Okay, so our initial here would actually be 8, right?
Yes.
If I plug 1 in, I'm going to get 8. So the sum of all of those would be 8 over 1 minus 0.8. I'll call it 4/5. Okay, whatever you're taking to the nth power is your r. So in this case, 4/5. So it's 8 over 1/5, or 40 would be our answer. So if we added all infinite amount of them, you would get 40 for an answer. All right, so, there's another example in your notes. 10 times 2/3 to the n. Let's see if I can find the camera. So the initial there is 20/3 when you plug in 1. And your r is 2/3, so we get 20. And it converges. So converge means you get a finite number. Okay, so what about over 4 to the n plus 1? So what's that one going to look like? So this is out of your notes too, but I'll just write it down. So it's 3 to the n over 4 to the n plus 1. So if I'm not sure what that's going to look like I don't even know what r is there because I've got an n over n and n plus 1. So let's just start by maybe writing out a few terms. That might help, or we could algebraically manipulate it, another way to do it. So if I plug in 0, I'm going to get 1 over 4 to the first, so it's 1/4. And this sigma notation implies that we're adding them all up. So 1/4 plus, now I'm going to plug in 1, I get 3 over, plugging in 1 here, 16. And then if I plug in 2, I get 3 squared is 9 over 4 cubed, which is 64. So from this, well, we already know what our first term is. What are we multiplying by?
Three-fourths.
Good, 3/4, because the top is multiplying by 3 and the bottom is multiplying by 4. So our r is 3/4. So we have enough information just kind of figuring it out that our first term over 1 minus our r, which is 3/4. So I get 1/4 over 1/4, and we add up to be 1. So our answer would be 1. I know that I can do that because my r it's an infinite series, and r is less than 1. R is going to be 3/4 here. Another way we could have done it, if I have 3 to the n over 4 to the n plus 1, I'm going to go 3 to the n over 4 to the n times 4, that's 4 to the n plus 1. This is 4 to the n plus 1 because that's 1. So then you could think of that as 3/4 to the n. Then I got a 4 on the bottom, so times 1/4. So it's 1/4 times 3/4 to the n. Then you can see a little better that your initial is 1/4 and your r is going to be 3/4. Couple ways to look at it. Okay, so I showed you how to do it in a calculator. I'll never show you that. If you wanted to do it on your calculator, there's a whole bunch of keystrokes, the sequence, and all of that. I'm not going to spend any time showing you how to do that. And if it's supposed to go to a infinity, I suggest to go to 200 and see what you get. Okay, so my next page is the separate sheet. I just noticed today that that is not in your notes, so it belongs between your first and second page. The power series sheet. So I suppose, I don't even think I posted the notes, huh guys, at home? I'm so unorganized today. So I'll do that. Let's hope I scanned them and put them in my drive. I thought I did that. I haven't, so I'll get those to you later on. Okay, so power series, it's an infinite series whose terms contain successive positive integral, meaning integers, powers of a variable. Okay, so that definition is confusing. A geometric series is what we've been talking about. It's like if you're multiplying by the same thing every time, that's called a geometric series. A power series, kind of a more vague version of the geometric series. Power series have x's in them, and if you assign x to be a number, then many times they become a geometric series. So a geometric series usually just have numbers in n's. Power series have x's. Keeping them apart is not all that important either. Okay, so here's an example of a power series. It's centered at 3. You can tell that it's centered at 3 because it's x minus 3. And whatever makes that 0 is the center. You could also say it varies around 3. I'll call it the center more than varies around 3. So you're going to be asked, kind of like we did with integrals, does this series converge or diverge? So if you get a number, it converges. And it always is going to be, your question will be for this one, where does it converge? Because it always converges at the center, no matter what. So the question will be, does it converge elsewhere? What is the interval of convergence? Well, in order for a geometric series to converge, the ones we talked about in our notes here, r has to be less than 1 in order for it to converge. So if we're taking x minus 3 to the n, then that x minus 3 has to be less than 1, or between -1 and 1. So if I want to figure out where it converges, I would say, well, in order for it to converge, that has to be greater than -1 and less than 1. Okay, so then we just solve that inequality. I'm going to add 3. So I get 2, 4. So the question would be, where does it converge? It converges if x is between 2 and 4. It doesn't converge if x is greater than 4 or less than 2. good video footage of me taking a drink there. Okay, so our interval of convergence is 2 to 4. We just found the interval of convergence. So we'll get a number as long as x is between 2 and 4. What's the center? The center is always right in the middle of the interval. So if you can find the interval of convergence, 2 to 4, you can look at that and know that the center is 3. Well, we knew that just based on the way the series was written, because it's x minus 3. X minus 3. But it was supported with the fact that the interval is from 2 to 4, which makes our center at 3. You'll also be asked what the radius is. Well, the radius, think of it on a number line, from 2 to 4. If my center's at 3, think of this as like a circle, radius. How far do I go in each direction from the center to the end of our interval of convergence? You can see that our radius is 1. And our center is 3. So I don't think that you'll be doing any of these types of problems in the 9.1 assignment. Those might even be like 9.3, 9.4 types of questions, but I'm just prepping you for there's going to be overlap from one section to the other, like we'll be doing the same thing. 2 and 3 are similar, and 4 they're similar types of problems. Okay, so back to the notes. This is just showing why it converges at 3. It actually makes up some math, some weird math. So we said that it's assumed to always converge at 3 because that's the center. Because if you plug 3 in, you're going to end up getting 0. And you're going to end up getting 4 times 3 minus 3. So you're going to get 4 times 0 to the 0. And we know that 0 to the 0 is indeterminate, but in this case, it's convenient to just say 0 to the 0 is 1. Kind of like earlier today, we talked about factorials. 2 factorials, 2. 1 factorial is 1. 0 factorials, what? What's 0 factorial?
0.
It's 1. Because it just works better when it's 1. So in this problem, it works better assuming that 0 to the 0, I don't know what the proof is, but it is 1. Okay, so moving on, if I assigned our x to be 5 here, 5 minus 3 is 2, so we get a geometric series of 4 times 2 to the n. So that's one example of a geometric series. That's when x is equal to 5. So notice, does this converge?
No.
It doesn't. How do you know it does not converge?
It's not less than 1.
Your r is 2, which is not less than 1, right? Or it's not between -1 and 1. So it diverges. It goes to infinity. Okay? And that's when we use 5 for x. And we've noticed our interval of convergence is between 2 and 4. So if you pick a number between 2 and 4, it's going to converge. If it's not, then it's going to diverge. All right, so now kind of applying what we have learned. This is out of the book, page 461. We're going to do 4 problems from that. Page 461, I can either put them up here or you can open your books. So a lot of what the purpose of chapter 9 is, it's a confusing thing where like you get in the middle of chapter 9 and you're like doing all the work, but it really doesn't always make sense why we're doing. Like, why do we need to know series and things like that? So what we do is we want to, a lot of times in this chapter, we're going to have certain expressions or equations that are not very workable. Like, we don't know how to find the antiderivative of it, or the derivative of it is tedious and the second and third derivatives are brutal. So what we can do in math is represent certain expressions using polynomials or series that are much more workable. And they're polynomials like this. We can find a derivative really easy because it's a power rule. We can find a second derivative really easy because it's another power rule. So they're more workable expressions representative of what we had before. So now, right now, these are still pretty easy, like what we're representing 1 over 1 plus x. Well, 1 over 1 plus x is not a terrible thing, but we will get worse problems that greatly benefit us by representing them with these polynomials. And that's what 9.2 we're going to get into, called Taylor polynomials, and so on. So much of this chapter is figuring out how to represent expressions with series. And if we do have an expression or a series that represents it, does it work for all x? Well, it only works for the x's that are in the interval of convergence. So we'll talk more about that in the future. So number 1, find a power series that represents 1 over 1 plus x. And they're giving us the interval from -1 to 1. Okay, so the 1 over 1 plus x, that's getting back to our expression a sub initial over 1 minus r. So they're telling us it's 1 over 1 plus x. So what do you suppose the initial term is? Rhymes with fun.
1.
It is 1. So if we're using this as our formula, our initial is going to be 1. So if I wanted to write this as a polynomial, it'd be 1. And then what's my r here? What are we multiplying by? It'd be negative x. Because 1 minus what will give me that negative x? So we're multiplying by negative x every time. For 1 is my first term. My next term would be negative x. So, and then we're multiplying by negative x again, so it'll be plus x squared. Multiplied by negative x again, it would be minus x cubed, and so on. If I wanted to write, so that's one way of writing it.
Why we're multiplying by negative x?
So if it was like 3, well, the question was, why are we multiplying by negative x? If I had 3 over 1 minus 7, your initial term is 3, right? And your r is 7. So if it was 3 over 1 plus 7, your initial would be 7, your r would be negative 7. Since it's plusing, we're adding, it's always the opposite.
Okay, but like, how did you get like any of this?
This is a problem. They tell us that.
It's just the formula of a bunch of
They say represent this as a polynomial. Or does it say a power series?
I thought that one was the geometric one.
Yeah, that's what power and geometric are basically the same thing. Powers are geometrics with x's in them. Think about that. Okay, so we could write that out. That is in answer. If I wanted to write it in sigma notation, we could write it as n equals, we could start at 0, we could start at 1. I'm going to start at 0, and we're going to go to infinity. So my first term, I'm multiplying, well, my initial is 1, my multiplier, my r is negative x. If I put n here, does that work? Does that generate those terms? It does, because if you put 0 in, that's going to give you 1. Notice, if I had 1 here, it wouldn't work unless you put n minus 1. Then it would work. So there's different ways of writing the same thing. So I'll write that. So if I did from 1 to infinity of 1 times negative x to the n. That's not going to work because I plug 1 in, that's going to give me my second term, and then my third, and so on. To get that one, we could go n minus 1. Now it would work. So these are identical, same thing.
Are they gonna make you write it in a certain notation on the exam, or will it not matter?
Jason asked if they're going to write it in a certain notation. Either one would be right in my class and on the AP exam, because they're literally identical. But a lot of times they'll say include the nth term. So we did not include the nth term. So we would say negative x to the n, and so on, and that would be, now it would be identical. All right, so that was number 1. Why don't you try it with x over 1 plus x.